Hey everyone, welcome to the next lesson in our Cosmic Adventure lecture series. My name is Dr. Valerie Rapson, Assistant Professor of Physics and Astronomy at SUNY Oneonta and past Director of the Dudley Observatory. Today we're going to talk all about deadly asteroids and the DART mission. It seems like every couple of months there's another news story about a deadly asteroid that's hurtling towards Earth, and 99% of the time it's really no big deal. The news always seems to hype it up a little bit more than they really need to. But the truth is, there actually are some dangerous rocks out there that we should be watching and tracking, and we should also be planning for a potential impact. We need to have a game plan to protect ourselves or maybe stop the impact if we're able to. So that's really what we're going to talk about today. We're going to talk about the asteroids that exist in our solar system, where they are, and how much danger they actually pose to Earth. And we'll also talk a bit about the discovery methods. How do we find and track these asteroids? Then we'll talk about this DART mission, which launched late 2021, that is really an asteroid mitigation mission. We're testing out some techniques to potentially nudge an asteroid out of the way if it was on a direct collision course with Earth. So we'll start with a brief overview of asteroids, what they are, talk about their dangers and how we track them, and then we'll get into all of the cool details of the DART mission and talk about the results that we hope to see in late 2022. Let's start with a brief introduction to asteroids. Asteroids are really just rocks that are orbiting around the sun in our solar system. They're basically the leftover bits of planet formation 4.5 billion years ago, and they're made mostly of rock and metal that never ended up inside of one of the planets and didn't get close enough to the sun to fall in. With modern day technology and telescopes, we can take pictures of these objects and even travel to them to learn a lot more about them. Here on the right, you see a bunch of pictures of different sized asteroids, and they're shown sort of roughly to scale just to kind of give you a sense of how big or how small they can be. The large one in the middle of the screen there, this is 21 Lutetia. It's a couple hundred miles wide, and they get as large as a few hundred kilometers or a few hundred miles wide, all the way down to maybe a mile wide or even smaller in some cases. Dactyl up here is only about 2 or 3 miles wide compared to, again, hundreds of miles for the largest one. So they really do range in size from really big to really small. We've been able to study these asteroids by traveling to them and also by studying meteorites that end up on Earth. And we found that most of the asteroids are primarily composed of rock and metal, like nickel and iron. Depending on the type of asteroid, you might also find some minerals in there as well. But you can basically just think of these as hunks of rock and metal that are orbiting around the sun amongst the planets. Now, the good news is most of the asteroids do not pose a danger to Earth. And that's because they've kind of collected themselves in their own orbit between the planets Mars and Jupiter. We call this the asteroid belt, and you can see it in the cartoon on the right-hand side. Here we're showing the sun, our 4 inner planets and their orbits. Out beyond Mars, there is this ring of asteroids within the asteroid belt, and then you've got Jupiter, and further out, of course, are the rest of our gas giants. Now, asteroids can exist at any location in the solar system, but many of them are in the asteroid belt. And this is because of what we call a resonance. So each of the planets orbiting around the sun in our solar system sits in a gravitational resonance where the gravity between the sun and the outer planets basically makes that distance from the sun a prime location for rock and gas and dust and material to collect together. And that's why a planet formed in that location and is now orbiting the sun in that spot. The spot between Mars and Jupiter is another resonance, and in this location, it seems like a planet never formed. For whatever reason, the material never ended up sticking together, creating another planet. So what we see is a location where all the leftover bits of the solar system seem to collect between these two planets. Now, there are also a large chunk of asteroids at the same location as Jupiter. You can see marked here the Trojan asteroids. These orbit the Sun in front of and behind Jupiter. And the way this works is since they're at the orbit of Jupiter, they're orbiting around the Sun at basically the same speed. So Jupiter will never catch up to the asteroids and crash through them, or vice versa. The asteroids are never going to catch up to Jupiter and crash into them. They will just orbit the Sun in front of or behind Jupiter and go around at the same rate as the planet does. Thinking about all of the asteroids in our solar system, there's over 1 million cataloged asteroids, but there's probably many more. Some of the small ones are really hard to detect, so some astronomers think that there could be as many as 150 million asteroids spread throughout the solar system, and we've only detected and found 1 million of those so far. Now, we said that asteroids can exist in any location, and the ones that are at Jupiter's orbit and the ones in the asteroid belt really are not something that we have to worry about from a danger perspective. The ones that we do have to worry about are called near-Earth asteroids, or NEAs. Basically, a near-Earth asteroid is any asteroid whose orbit is primarily in the inner solar system, amongst our rocky planets, somewhere between Mercury and Mars. If you want to get specific about the definition, NEAs technically have a perihelion distance, or they have a closest approach to the Sun, of less than 121 million miles, or less than 1.3 times the Earth-Sun distance, or 1 AU. Now, near-Earth asteroids, just because they are in the inner solar system, doesn't mean they are necessarily dangerous. A near-Earth asteroid might not ever come close to Earth. It might not cross Earth's orbit around the Sun. It just happens to be, relatively close to the Earth or near to the Earth compared to those in the asteroid belt or further out in the solar system. The animation you see on the bottom there is a model showing all of the known near-Earth asteroids that were discovered between 1998 and 2018, so about 20 years of data. You see the Sun at the very center of the solar system. We've got Mercury's orbit in orange, Venus in purple, Earth in white, Mars in red, and all of the blue dots there, those are all near-Earth asteroids. So you can see that it's quite a crowded space, and we keep discovering more and more. As of 2022, we've discovered just over 28,000 asteroids of various sizes, and these are all, the ones that are near Earth. And with modern technology, our space and ground-based telescopes, we actually have an average detection rate of about 40 per week, which is a little bit scary, but also really good, right? We're detecting these asteroids so that we can track them going into the future. Now, astronomers like to classify objects based on their size and shape and orbit, and that's exactly what they've done with near-Earth asteroids. There are 4 main categories that classify near-Earth asteroids based on the location of their orbit, and it also helps us get a sense of just how potentially dangerous a near-Earth asteroid can be. So let's go through the 4 different categories here. First, we have the Amors. These are near-Earth asteroids whose orbit is primarily outside of Earth's orbit. So in our little cartoon here, which is totally not to scale, you've got the Sun in the middle, the solid black line there, that's the orbit of Earth, and the orbit of a theoretical Amor asteroid is this lighter black line out here. So basically, the orbit is exterior to Earth, but interior to Mars. It's not as far out as those in the asteroid belt. The Apollo class of asteroids, these are Earth-crossing near-Earth asteroids. So what does that mean? Well, if you look at the cartoon here, you can see the orbit again of planet Earth. But notice that the orbit of the asteroid actually crosses the path that the Earth takes around the Sun in 2 places. This doesn't mean that the asteroid is on a collision course with Earth, but it does cross the same path that the Earth takes. So in theory, if the Earth and the asteroid were in the exact same spot at the right time, they could collide, but most of the time they generally don't. You know, the Earth will be many months away from passing that spot as the asteroid moves by. But basically, the Apollo asteroids, they are on an Earth-crossing orbit, and they have a semi-major axis or average distance from the sun larger than that of Earth. So they generally go, far away from Earth, but not quite out to the orbit of Mars. The Attends are also Earth-crossing near-Earth asteroids, but they have a smaller semi-major axis, a shorter orbit around the sun. Their orbits might look something like this, where they get relatively close to the sun, then they come back out and pass Earth's orbit twice, and then loop back around the sun. So they tend to orbit around the sun faster than planet Earth does. And these are also potentially dangerous as well, right? Because they're going to cross Earth's orbit, so we really need to keep an eye on those. And finally, the Asteroids on the bottom, those are asteroids whose orbit stays within the orbit of Earth around the sun. So basically, they might potentially strike Venus or Mercury someday, but they don't pose that much of a threat to Earth because their orbit is always interior to planet Earth. So these are the 4 different categories of near-Earth asteroids. And I know I've said this like 6 times already, but just because something is a near-Earth asteroid doesn't mean it's necessarily dangerous. But there is a separate category of potentially hazardous asteroids, which are the ones that we really need to focus on because they have the higher probability of striking Earth and potentially causing some damage to our planet. So let's take a look at these PHAs, or potentially hazardous asteroids. And I'll apologize ahead of time. You're definitely going to be overwhelmed by acronyms by the end of this presentation, but that's just life in astronomy. So we'll keep moving forward here. PHAs, or potentially hazardous asteroids, these are large asteroids which come very close to Earth's orbit around the sun. Technically, a potentially hazardous asteroid is at least 500 feet wide, and it comes within 0.05 AU, or 4.5 million miles of Earth's orbit. Note that it doesn't have to come within 4.5 million miles of Earth itself, but it just has to come within 4.5 million miles of Earth's orbit, or potentially even cross Earth's orbit. On the right-hand side, we have a chart from NASA that shows all of the near-Earth asteroids discovered, and then breaks the potentially hazardous asteroids into 2 categories. Those that are 140 meters or bigger, that's the 500 feet wide ones, and those that are really large. We're talking a kilometer or bigger, so those that are miles wide. And you can see here, it's basically showing discovery date and then cumulative number of asteroids discovered. And things really started to pick up in the late 90s, early 2000s. That's when we started to build large telescopes both on the ground and in space. And we really had the capabilities now to find these near-Earth asteroids. So it doesn't surprise me that we see a spike in modern day of detections. We should think of that as a good thing, not as a bad thing. But here, if we look at the total, you can see we're just over 28,000 total near-Earth asteroids. And then we've got them broken down here on the chart. Almost 10,000 are large and almost 900 are 1 kilometer or greater. But the potentially hazardous ones that actually do get close to Earth and are large, there's about 2,200 total and 161 that are greater than 1 kilometer wide. So you've got about 2,200 objects to stress about. That's basically what the chart is showing you here. The last number there, the NECs, is actually near-Earth comets. We're not going to talk too much about comets today, but theoretically they pose the same type of threat as near-Earth asteroids do. So we continue to find more asteroids, and we're going to track them and make sure that we can categorize and pay attention to exactly if and when they are going to be on a direct collision course with Earth. So now that we've introduced this concept of near-Earth asteroids and potentially hazardous asteroids, let's talk briefly about the impact. Just how dangerous are these large rocks? Well, we already know that a lot of material hits planet Earth on a daily basis. We find meteorites, we even know of large craters from large impacts in the past, but on a yearly basis, there's over 40,000 metric tons of small material that passes through Earth's atmosphere. Some of the larger chunks will make it to the ground, but most of it ends up burning up and not causing any issues whatsoever. But these larger, potentially hazardous objects are the ones that could make it to the ground and really cause a lot of damage. A rock that's about 500 feet wide, if it crashed into the ocean, any ocean, it would be the equivalent of detonating 8 million tons of TNT in the ocean, and modeling suggests that that would create tsunamis that would destroy all coastlines along that ocean. So that's definitely not good. And if we had a large impact, we're talking about a half a mile, that 1 kilometer or larger asteroid, that would definitely cause global devastation. Imagine that striking an ocean, you would create terrible tsunamis, you would likely create earthquakes, trigger volcanic eruptions, and then basically it's just a domino effect after that. It's not about the location where the object hits. Of course, if an asteroid were to strike a major city, that would be devastating, but it's really what happens after that. It's the earthquakes that then damage other locations. It's the volcanic eruptions that make our atmosphere toxic and dark and trigger this, death of plants and then animals and a cooling off of the planet. It's just not a good thing that would happen. So overall, we really want to monitor for these large objects because they are the ones that could cause the most devastation. We don't worry too much about the small ones. It's the big ones that we stress about. So now that I've got you all worried about, a potentially dangerous impact, let's talk about how we find these asteroids and how we track them. And hopefully that will bring you a little bit more comfort before we move on to talking about the DART mission. So here we've got a little video that shows a relatively recently discovered asteroid back in 2014. And the video shows the asteroid moving through our solar system against the background stars. That's basically how we detect asteroids with modern telescopes. If you take a telescope of any size and point it towards the sky, you're going to be able to see stars. If you point the telescope at the same patch of stars in the sky and track it as the night goes by, or track it day after day, evening after evening, you're going to see the same patch or the same pattern of stars. The stars are so far away that in our short lifetimes, their relative position is not going to change compared to one another. But objects in our solar system, like planets or asteroids, they are a lot closer to planet Earth, and they are going to appear to move against the background stars. So if you were to monitor the same patch of sky night after night, and you saw one object that appeared to move against the background stars, then you would know that that object is within our solar system. That's exactly what you see on the left-hand side. So all of the white circles are stars in the background, and the one white object inside the purple circle there, that's an asteroid moving against the background stars. We can track asteroids using small backyard telescopes or large professional telescopes, but the ideal way to do it, and the best way to find as many as possible, is not to use optical telescopes that pick up light that our eyes can see, but rather to use infrared telescopes. And the reason for this is because most asteroids are a lot brighter in infrared than they are at visible or optical wavelengths. If you take a look at the cartoon on the right, we're representing 3 different types of asteroids here. So imagine that you had an asteroid that was very lightly colored, more like chalk, an asteroid that's kind of a light gray, and an asteroid that's really dark like charcoal. The different color of the asteroid means that it's going to have a different albedo, or it's going to reflect a different amount of sunlight. Intuitively, you probably know that a light-colored object is going to reflect the most light, and it would look really bright in our pictures. But as we get to the darker asteroid, even if it was really large, its dark color is not going to reflect a lot of sunlight. So the darker asteroid is going to be trickier to see with a standard telescope. And unfortunately for us, most asteroids really fall kind of between these two categories here. They're light gray to almost black in some cases. So visible light is not ideal. These asteroids are not going to reflect too much sunlight, but they are going to emit a decent amount of infrared light. Infrared light is often thought of as thermal radiation. Basically, these asteroids are dark. They are going to absorb sunlight, especially those that are close to the sun, and they are going to re-emit it at infrared wavelengths, so they're going to look warm. So in the bottom example, you can see that these three asteroids that are different colors all look pretty much the same in infrared light. They're all about the same temperature, so they would all be easy to spot with an infrared telescope. So as we move on and discuss the different missions that are looking for them, you're going to see infrared pop up frequently, and that's for this exact reason. Asteroids just generally look brighter at infrared wavelengths and are therefore easier to detect. So let's talk about some of these missions in a little bit of detail. One of the main missions that has discovered tens of thousands of asteroids for us is called NEOWISE. NEOWISE stands for Near Earth Object Wide Field Infrared Survey Explorer, and it was the idea was based off of the original WISE mission. So there's one telescope called WISE. It was launched in 2009. It is an infrared observatory, and it was designed to do what we call an all-sky survey. Basically, pan around the sky, take pictures of the entire night sky in the northern and southern hemisphere, and do it in the infrared. This would allow astronomers to find all sorts of different objects that glow at infrared wavelengths and do all sorts of science. Everything from star and planet formation to supernova explosions, galaxy studies, all of that type of stuff. That's the reason that WISE was put into orbit. But infrared telescopes and their cameras on board, they have to be cooled. So we have to send cryogen with them. And often the cryogen will run out relatively quickly, within a few years' time, and then the telescope isn't fully functional, at least not for the purposes it was originally designed for. The NEOWISE mission basically repurposed the WISE telescope and uses one band of infrared that is still functional on the telescope to take pictures of the night sky and basically search for asteroids that we have never seen before. The picture on the right is a photograph of an asteroid called 872 Holda. And what you see here is basically a composite image of about 15 or 20 pictures that were stacked on top of each other, all of the same patch of sky. So when you look at it, you see a bunch of white dots, a bunch of stars. And then this red dot that seems to move against the background stars in these images, that is your asteroid. So we're looking here, in this case, at an example of an asteroid detection in the main asteroid belt. This is not one of those near-Earth asteroids. But WISE is useful for finding all different types of asteroids. It's taken over 1 million images of the sky, and within those images, we've discovered over 40,000 different types of objects in our solar system. Asteroids, comets, all types of stuff. Even a few moons of the gas giant planets, I think, were discovered with WISE as well. So WISE is really helping us find and track some of these objects, and it is a space-based telescope. Another useful ground-based telescope is the Infrared Telescope Facility, or IRTF. IRTF, and you can see a picture of it there on the bottom left, is a ground-based 3-meter telescope on top of Mauna Kea, Hawaii. So it's with all of those other large telescopes in Hawaii. And it's not a dedicated asteroid hunting mission. It's an infrared telescope that is used for a variety of different sciences, but it can provide targeted observations of asteroids when needed, and it can also act as a rapid response telescope for newly discovered near Earth asteroids. So if WISE or some other telescope finds a near Earth asteroid, and we really need to know, exactly what its trajectory is or how large it is, IRTF can essentially drop everything, point itself towards the asteroid in the sky, and give us the information we need to make sure that this asteroid is not on a direct collision course with Earth. Being a larger telescope, it does have a little bit more power, so it can see the asteroids better, and it can actually take spectra of them as well. So on the right-hand side, you see an asteroid and a spectrum. It was taken back in 2004. But what you're looking at here is different infrared wavelengths of light and the normalized reflectance, or basically how bright the asteroid looks at those different wavelengths or different colors. And we can look for absorption features here, or drops in light, really. This happens to be due to olivine, a mineral that is within a lot of asteroids in our solar system. And by studying this, we can get a sense of the type of asteroid, basically what it's made of. We can also get a sense of the density of the asteroid as well. And that's going to be really important when we talk about mitigation, right? If we need to blow up an asteroid or move it out of the way, or do something, we need to have a sense of how big it is and also how dense it is. So we'll know how much power it takes to affect the asteroid in the way we want it to. So IRTF can do a lot of cool scientific studies of asteroids, but it's really designed to be more of a targeted mission. It does find new asteroids occasionally, but it's used more for follow-up of known objects. So NEOWISE and IRTF are the two main asteroid hunting and studying telescopes, but there are a whole bunch of other telescopes and sky surveys that are happening across the world that are also detecting a ton of asteroids. Here I've listed a handful of them. We've got the Catalina Sky Survey, PanSTARRS, the Panoramic Survey Telescope and Rapid Response System, ATLAS, or the Asteroid Terrestrial Impact Last Alert System, and LINEAR, the Lincoln Near Earth Asteroid Research Project. So basically, acronym upon acronym for telescopes and projects that are designed to find new asteroids in the sky. On the right, you can see a familiar image there, basically a little video of a new asteroid discovered in 2020 by the Catalina Sky Survey. Again, moving against those background stars, triggering us to study it more and identify it as an asteroid within our solar system. So between all of these sky surveys that are literally monitoring as much of the sky as possible over and over again, combined with WISE and IRTF, astronomers think that they've discovered about 90% of all of the large asteroids, so larger than a kilometer or about 3,200 feet, while only 40% of those greater than 500 feet have been documented. So this is both a little bit comforting and a little bit unnerving all at the same time, right? We think we have discovered and have the ability to track all of the asteroids that could cause potential global devastation, but there's still probably 60% of the total asteroids that are still dangerous but maybe won't destroy the whole planet that we have yet to discover. Part of that is just due to the time that the telescopes have been functional and their telescope capabilities. And we're focused now on trying to find as many of these as possible. You saw on that previous graph the spike up in the last 10 or 15 years of our detections, and I think the graph and the total number of discoveries is only going to increase from here. But with this information, now that we know a bit about asteroids and how we find them, you probably have a legitimate question running around in the back of your mind. And that question, of course, is, are we doomed? right? We found all these asteroids, but I've yet to really tell you if any of them are truly dangerous, if they truly pose a threat to our planet. We know that asteroids have struck the planet in the past, both large and small. There have been multiple that have, in the last 100 years, either crashed or exploded over Russia. And of course, everybody knows the story of the poor dinosaurs, where the comet or asteroid struck the Yucatan Peninsula and basically wiped out much of life on this planet. So it's possible that this could happen again. We have to be honest and realistic about it. But let's take a look at the current known dangers. What do we know, and should you be really nervous about it? So you can go online to NASA's website. Here's the specific website if you're interested, if you want to jot it down. But you can track it at any time the list of the most dangerous, potentially hazardous asteroids, and you can get some basic information about them. I took the list and I sorted it from most dangerous to least dangerous and took a little snapshot of the first 10 or so asteroids on the list. So here what we have is object designation, that's the name of the object, the year range in which it would potentially strike planet Earth, the number of potential impacts, so either how many times it's going to come around and strike, or if it's a multiple object system, there might be more than one strike. The impact probability, what's the percent, the chance that it's actually going to hit the Earth. The speed that it would strike at, H magnitude, which is how bright it is in the infrared, its diameter in kilometers, and then some numbers over here. The Palermo and Torino scale are two different ways that astronomers classify how dangerous an asteroid is. Basically, bigger numbers are more dangerous. The Torino scale goes from 0 to 10, with 0 being don't worry, 10 being duck and cover right now. And the Palermo scale is a little bit different. It has negative and positive numbers, but the larger the number, the more dangerous the object is. Sorting by most dangerous, the top one there, 2020 AE1, that has the potential to impact actually relatively soon, and that's why it's on the top of the danger list there. But the impact probability is really low, 6 times 10 to the minus 4, so far less than a 1% chance that it's actually going to strike. And it actually is quite small. It's only about 0.07 kilometers wide, so relatively small on the potentially hazardous scale. So while it does have a Torino number of 1, it's probably not going to strike, and even if it does, it wouldn't cause all that much damage to our planet. If you go towards the bottom of the chart here, this one actually happens to have the highest impact probability. It's not necessarily the most dangerous because they take a bunch of things into account when they measure the danger, but it does have a 4.7% chance of striking our planet. The good news is it isn't going to hit until sometime between 2095 and 2121, so we've got 80-ish years to figure something out to protect ourselves. And if we look over here at the size, it's also quite small, even smaller than the first one that we talked about. So hopefully this puts you a little bit at ease, right? You should breathe a sigh of relief after looking at this list, and you can check the list anytime you want. There really isn't a large object that's definitely on a collision course with Earth anytime soon. So even though we're not in imminent danger, we still should have a plan for the future, right? We never know if we're going to discover a new large asteroid that we didn't know about, or if one is going to have its path altered and all of a sudden be on a direct collision course with Earth. We really should have some options available to us. And we'd be here forever if we talked about all the possible options. So I'm going to cover 3 options here. And these are 3 options that have been primarily suggested to us through science fiction films or television shows. So our first option, of course, is to just duck and cover, right? Pretend it's not happening, duck and cover, hide, and see if we can ride it out. That was kind of the idea of the new show, Don't Look Up. If you haven't watched it yet, you should definitely check it out. But basically, the characters discover that a comet is on a collision course with Earth, and most of the world just pretends it's not happening. They ignore the scientists, and they don't even really plan or try to save themselves. They just ignore the whole thing. That's probably not the best option to choose, but it is theoretically an option on the list. Another option, which we have seen in multiple movies, is to blow it up, right? Your first instinct might be go up to the giant rock, put some explosives in it, and blow it to bits, right? Did it in Armageddon, did it in multiple other films after that. That could be a way of destroying the object and hoping that it wouldn't cause as much damage to Earth. That one is not on the top of scientists' list, mostly because if you take one object and blow it up, you have now taken one large danger and turned it into many smaller dangers. And having a forceful enough impact or explosion to push all of the material out of Earth's direct path is a lot trickier than it sounds. So blowing it up, probably also not the best option. So a slightly better option that the NASA and other space agencies have been focused on recently is to push it out of the way. Now, I haven't seen a science fiction film that covers this option quite yet, but there is a really great episode from SpongeBob, if you've got kids or grandkids that watch SpongeBob. And basically what Patrick the starfish there is doing is saying that they should take where they live and push it somewhere else. Now, in the cartoon, they're not in danger from an asteroid strike. They're in danger from a giant worm coming to destroy their city. But that's not the point. The point here is that, instead of pushing Earth out of the way, maybe we could go up to the asteroid and push it out of the way. That seems like a relatively reasonable option that if we do it properly and know far enough ahead of time, we can just nudge it out of the way and it will never hit Earth. It'll safely fly by, and hopefully we won't have to worry about it anymore into the future. So that's where the DART mission comes in, the second half of our lesson here. DART stands for the Double Asteroid Redirection Test, and it's exactly what we just talked about. It's a trial run to push an asteroid out of the way. So here's basically what's going to happen. The spacecraft launched already on November 23rd of 2021, and it is traveling outwards towards a binary asteroid system. I'll tell you all the details about that in just a moment. But the spacecraft is ultimately going to travel to this asteroid system. It's going to collide with a moonlet, a small asteroid that is orbiting a large asteroid. And the collision of this spacecraft with the asteroid is going to change the orbit of the moonlet around the main asteroid. Now, this asteroid pair is not on a collision course with Earth. If it doesn't work, we're not doomed or anything like that. We're literally just testing out the idea. If I crash into an asteroid, can I do it in the right way with enough force to actually push it and change its direction, or in this case, change the orbit of the moon? That's what we hope to find out. So this theory of pushing an asteroid out of the way is scientifically called the kinetic impactor technique. Basically, you are imparting momentum and energy onto the asteroid. It now has a change in kinetic energy. Its motion will change. And if this were a threat to Earth, hopefully its direction and path would change and just pass by our planet. So from here, what we're going to do is talk briefly about the asteroid pair that DART is traveling to. We'll talk briefly about some of the technology on DART, and then kind of wrap things up with what we hope to see in the future. So here's the target. The pair of asteroids are called Didymos and Dimorphos. Didymos is the main body. It's about 2,500 feet wide. And Dimorphos is the moon, or moonlet as they call it. It's much smaller. It's only 530 feet wide. It is a near-Earth asteroid system. I'll show you the orbit of it in just a moment. But on the right, you've got a cartoon showing what the asteroids probably look like up close. And on the bottom here, you have some neat radar images from Arecibo. The Arecibo Radio Observatory, before its collapse a few years ago, actually had the ability to send radar signals out into space, which would bounce off of planets or asteroids, and it would allow us to detect those signals back and map the shape and distance to these asteroids. So what you see in the picture here, this is multiple compiled images of the same object. Didymos is on the bottom, the main asteroid, and the little white speck that you see up there, that's the moonlet, that's Dimorphos. And within its orbit around the asteroid, it changes position, which is why you see it getting a little bit higher up there. Dimorphos takes about 11.9 hours to orbit around the moon. And when we collide with it, we hope to change that orbit, actually push it in closer, make it orbit a little bit faster, and measure how much of an impact our impactor actually had on this moon orbiting the asteroid. So we've taken pictures of it before, we have some models, but we've never traveled up close to this asteroid yet. So DART will actually give us our first up close pictures of what these things look like as well. Now the orbit of Didymos and Dimorphos is shown here. This is one of those Amur type near Earth asteroids. So it stays primarily orbiting beyond the orbit of Earth. So if you look at the cartoon here, here's the Sun, Mercury, Venus, Earth is dark blue, Mars is red, and Didymos' orbit is the white. So it doesn't actually cross Earth's orbit, although it comes very close. And then it actually travels out a little bit farther past Mars, but not all the way to the asteroid belt. The orbital period is just over 2 years, so 770 days. And it's potentially hazardous because it gets so close to Earth's orbit, but it's not on a collision course with Earth. I want to emphasize that we are safe. This is not on a collision course with Earth. We're not trying to deflect the asteroid for our safety at the moment. We're just testing out this method for potential future dangers. So that's the target. That's where DART is headed. Let me show you some of the cool technology and techniques that are being used on this mission. First, whenever you send a spacecraft somewhere, you have to have an engine and you have to have a way to power the spacecraft. So DART is equipped with this new roll-out solar array technology. It's called ROSA, the roll-out solar array. This technology was actually tested on the International Space Station, and that's what you see in the video in the bottom. This solar array is attached to the space station, and in the repeating video, you just see it being rolled out like pie dough, basically. So the solar array is very thin, but also highly effective, and that is what is being used to power the computer and the onboard instruments to the spacecraft. There is a portion of ROSA that has been outfitted with really high efficiency solar array technology. And if that works well on this craft, I think that future spacecrafts will use this high efficiency technology, and we might be able to use solar panels on spacecrafts that travel, further out beyond the orbit of Mars and even Jupiter in our solar system. So that would be a really cool result if it works well. The engine is actually not a liquid rocket fuel engine or anything like that. It is the Next-C xenon ion thruster engine. This is technology that was used on the Dawn spacecraft that went to the asteroid belt and actually studied some asteroids up close there a few years ago. But this ion technology, basically what you do is you use electrostatic forces to accelerate, in this case, xenon ions out the back of the spacecraft. And then physics means that physics says that if you're pushing material out one end, that's going to propel the spacecraft forward. So basically, you don't have to expend hardly any fuel to get a spacecraft moving really high speeds. These ion engines are incredibly efficient, And this next C1 is kind of the latest and greatest ion thruster engine. So all is seemingly well so far, but this is another good test of this ion thruster technology. So lots of new tech to power and move the spacecraft. Also on board is really one scientific instrument along with a CubeSat, or basically a small satellite that was traveling along with the mission. The main piece of science technology there is Draco. That stands for the Didymos Reconnaissance and Asteroid Camera for Optical Navigation. Basically, it's just a camera, right? It's an onboard camera that is going to take photographs of the spacecraft, or photographs of the asteroid system, and also help with navigation. We'll talk about in a moment how the spacecraft is going to navigate itself to strike Dimorphos, but Draco is going to play a huge role in that. Once the spacecraft is really close to the asteroid, it's going to stream back images at the rate of 1 per second. So we're going to get a ton of cool pictures and information from this camera. Now this CubeSat here, this is called the Licia Cube, or the Light Italian CubeSat for imaging of asteroids, designed by the Italian Space Agency. That's going to be released about 10 days prior to the actual collision, and the CubeSat will not collide with the rest of the spacecraft. The rest of DART will literally just crash into the moonlet, but the CubeSat will stay in the system. It will take pictures of the collision, and it will even be able to turn and get images of the backside of the moonlet, which is not something that DART itself is going to be able to see. So the CubeSat's going to provide us with vital information about the actual collision, and also show us essentially a 360-degree view of the moon and the asteroid. So that's it for technology. You know, this is not meant to be a fancy science mission. We're literally just taking pictures, and since the spacecraft is designed to crash and be destroyed, they weren't going to spend too much money and put too much more tech on board this spacecraft. So far, things are going well. We've actually received a few images back from Draco. The spacecraft is not going to arrive at the system until September or October of 2022, so we don't have images of the asteroid system yet, but we do have a couple lovely images of star fields that Draco has seen here. This is the starfish cluster, or M38, I believe is the Messier number. But this image is taken basically to make sure that after launch, the camera and the onboard computer were functioning. And they also need to calibrate the camera, right? They needed to see what the spacecraft orientation was. They needed to see how bright the stars were to be able to calibrate the brightness of the camera, and also characterize any optical imperfections. Was there any damage to the camera? Are there any bad corners or pixels on the camera that will cause the navigation to be more difficult later? We really, as you'll see in a moment, need to have a high quality camera and fully understand any defects of the camera for the navigation portion to work properly. So let's talk briefly about this navigation system. DART is going to autonomously navigate to Dimorphos. We have, given it the oomph, the push that it needs to go there, but now it's going to do most things on its own. Once the spacecraft arrives at the system, and by arrives I mean is about an hour out, it's going to turn on this smart nav guidance technology, which is really based off of missile guidance algorithms. And it's going to autonomously correct so that it always is dead on heading towards Dimorphos. So here in the picture, what you see is just kind of a cartoon of the star field. Down at the bottom is what it might look like for the main asteroid and the moon. And once the two objects are identified, the smart nav system goes through this process. Draco will take images, that's what you see in the bottom left. This detection blobbing algorithm, which is, super technical, right? A blobbing algorithm. It basically looks for the two blobs. It identifies the large one and the small one so that it knows to head towards the small one, to head towards Dimorphos. It does some corrections, and it basically talks to the onboard thrusters, which then will fire the thrusters when needed and adjust the positioning so that the system basically functions on autopilot and automatically crashes into Dimorphos. So this is really cool, and it'll be a great test of technology that we've used on Earth, now using it in space. You might be wondering, why aren't we just guiding the system ourselves? Well, that has to do with light travel time. At the point where the spacecraft arrives at the asteroid, the time to send communications back and forth is actually going to be a couple minutes. And with that time delay, you wouldn't be able to adjust the spacecraft's position appropriately so that it would definitely crash into the moonlet. So we have to use this autonomous system to make sure that the collision actually happens as planned. So speaking of the collision, what's actually going to happen? Well, here we've got a cartoon showing Didymos and Dimorphos. Here's DART flying in. We've got LISHACube, the CubeSat, which has already been deployed. We're going to use that smart navigation system to head towards Dimorphos. It's going to crash into the moonlet. The crash is currently scheduled for sometime between September 26th and October 1st, depending on exactly how the traveling and the mission goes. And if all goes well, the impact speed should be almost 15,000 miles per hour. So there's going to be a lot of energy in the impact of this moon. So DART is going to collide with the moon, and it's actually colliding in the opposite direction that the moon is traveling. So notice in this cartoon that the moon is orbiting counterclockwise. We're going to crash into the moon, which is basically going to slow it down a little bit. And that slowed down motion means that the moon is going to shift inwards just a little bit to this new orbit, the dark blue labeled by the number 3 there. And if all goes well, we expect it to shorten the orbit. Now it's closer, it's going to orbit a little bit faster, so the time of the orbit is shorter. It'll shorten by a few minutes. And to actually figure out if this worked, we're not actually going to use anything associated with the DART system. We're going to have to use ground-based observations. DART is going to be destroyed, and the CubeSat is going to send us pictures, but the CubeSat is not designed to stay at the system and orbit and track the moon. It's just going to take pictures and keep going. So what we have to do is look at this system with large ground-based telescopes, see the main object in the moon, and track the orbit of the moon and see if its position and timing actually changed as expected. Once we have a good sense of whether or not things accurately occurred, then we'll know, how much force is required to change an asteroid's path by however much amount this asteroid changed. So that's the basic idea. We're going to send the spacecraft, crash into the moon. That'll cause the moon's orbit to get a little closer to the main body, and ground-based observations will confirm that it worked. So at the end of 2021, news came out that this was happening, and pretty much every non-astronomer friend I have asked me this question. Is there any chance that we are going to mess up and collide with this asteroid and accidentally push it into Earth's orbit? And that's a legitimate fear, right? We want to make sure that in our testing, we don't make a mistake and make something that's not a danger to the planet. But the good news is the chances of that are very, very slim. The momentum that we impart on the moonlet, the forces that are incurred, they're only changing the moonlet's orbit by less than 1%. We're not, flinging the asteroid and the moon out in a totally different direction in the solar system. The change in the moonlet's orbit is really not going to have much, if any, of an effect on Didymos, the orbit of the main asteroid. So that will stay in its regular orbit, which is not going to cross Earth's path at any point. And as we said, this is really designed to help us in the future. It's not designed to mitigate a current danger, but to help us plan for a potential future danger that we want to try and avoid. So I'd be willing to put my credibility on the line here and say, we're not going to send this asteroid hurtling towards planet Earth. All right, so to wrap things up here, I want to tell you about Hera. Hera is actually a follow-up mission designed by ESA, the European Space Agency, and it's going to visit the same system, Didymos and Dimorphos. It's going to be launched in a few years. It will visit the system in 2027, and it's going to survey up close the impact that the DART mission had on the asteroid system. So instead of me explaining this briefly to you, I'm going to call on a fellow astrophysicist you might know, Brian May, to tell you briefly about this mission, and then we'll wrap up our presentation here.
Hera is going to show us things no one's ever seen before. This ESA mission will be humanity's first ever spacecraft to visit a double asteroid, Didymos. This asteroid is typical of the thousands that pose an impact risk to our planet. Imagine a mountain in the sky with another rock about the size of the Great Pyramid swinging around it. That's Didymos. And just the seemingly tiny moon would be big enough to destroy a city if it were to collide with the Earth. But we're going to find out if it's possible to deflect it. This is going to be really, really hard. Aiming at a 160-meter wide target across millions of kilometers of void. Could we stop an asteroid hitting planet Earth? The dinosaurs couldn't, but we humans have the benefit of knowledge and science on our side. Hera is led by a multinational team of scientists and engineers, humanity's makers and doers. Right now, all we have is many years of research and theories, but Hera will revolutionize our understanding of asteroids and how to protect ourselves from them. First, NASA will slam its DART spacecraft into the smaller asteroid at more than 6 kilometers a second. Then ESA comes in. Hera will map the impact crater left by DART and measure the asteroid's mass. Knowing this mass is key to determining what's inside and knowing for certain whether we would be able to deflect it. Next come our briefcase-sized CubeSats. If you think of Hera like an aeroplane, then CubeSats will operate more like drones, able to take more risks, flying closer to the asteroid, carrying state-of-the-art science instruments, eventually touching down. The scale of this experiment is huge. One day these results could be crucial for saving our planet. Hera's up-close observations after DART's impact will help prove whether asteroids can be deflected, prove whether this is an effective planetary defense technique, so that if an asteroid ever poses a real threat to Earth, we'll be ready.
So you can see just how important this mission is as a follow-up to DART, right? DART is going to make the first collision, the first attempt at moving the asteroid, and Hera is going to kind of follow up to see just exactly how effective it was. So that wraps up our discussion about deadly asteroids and the DART mission. Hopefully you leave this presentation not stressed out, but comforted that astronomers and scientists are active in planetary defense. They are constantly monitoring for new asteroids, assessing their danger, and we now have real legitimate plans to mitigate any big potential threats we have in the future. So hopefully the human race will continue to survive and we won't go the way of the dinosaurs. Thanks for watching the presentation, and I'll see you next month.